So this is the 16th session in the subject of digital communications, and we continue our study of calculation for the bit error probability. In our last session, we had seen how to calculate the bit error probability in terms of the output of the filter. That is, if S1T is the input, we had seen that output was A1. If the input is S2T, the filter output was A2. And we had obtained the expression for the bit error probability in terms of A1 and A2. Now what we want to do is to obtain the expression for this bit error probability in terms of the input signals, that is S1T and S2T. That is what we want to do. So let us start. First of all, let us see what will be the nature of the matched filter for a binary receiver. Now note that the bit error probability is given by this Q function, where the parameter is A1 minus A2 upon 2 sigma n. Now we wish to reduce this bit error probability as much as possible, which means that we would like to maximize A1 minus A2. Remember, if the parameter of the Q function is larger, the magnitude of the bit error probability is smaller. So clearly the noise should be smaller and the difference of the two possible outputs must be as large as possible. So what it means is that we must maximize A1 minus A2, and since A1 is obtained when S1T is transmitted and A2 is obtained when S2T is transmitted and hence received, it is the difference that is to be maximized. Therefore, the matched filter that we design must be matched to the difference signal S1T minus S2T. Alright. So if we want to realize this matched filter, one way of doing it would be to obtain the appropriate transfer function based on this difference signal S1T minus S2T and then implement it. Another possibility is that we can use a correlation detector that we have studied earlier. And what we are going to do is to look at the correlation detector in this particular session. So remember that the correlation detector consists of basically a multiplier followed by an integrator. This is something we have studied earlier. So let me show you that diagram to you. RT is the received signal, which is either S1T or S2T. And this is the multiplier. The other input to the multiplier is the difference signal S1T minus S2T. So this of course has to be locally generated. And then output of this product is integrated, and that is ZT. Okay. And then this will be sampled and compared. We'll see that in a minute. But let us obtain the expression for ZT. So first of all, you have a product of RT and S1T minus S2T and then integration. So ZT will be S1T minus S2T multiplied by RT, and the whole thing is integrated over the bit time 0 to T. Now what we can do is we can expand this expression and rewrite this equation in this form. So instead of using a single correlator detector with a reference input of the difference signal, what we can do is we can implement two correlators, but each one has a reference input now. First one has S1T and the other has S2T. That's the difference. Okay, so both are equivalent, but this is the standard form in which usually this detector is built, because instead of generating S1T minus S2T and then feeding it as a reference signal, it's easier to generate S1T and S2T and feed it as a reference signal to two correlated detector. So this will look like this. So this is the received signal. It first goes through the top correlator where reference signal is S1T. The other one has a reference signal S2T integrated, and depending on whichever is larger, if the output of the upper arm is larger, you conclude that S1T was received, and if the output of the lower arm is higher, then you conclude. In other words, if ZT is positive, then you conclude that S1T was transmitted and hence received, and if it is negative, then you conclude that S2T was transmitted and hence received. Okay, that's how the circuit looks like. But what we want to do now is to obtain the expression for the bit error probability. So how do we proceed? Let us do that now. First, let us write down the equation for the bit error probability that we already derived in the last section. This is in terms of the output quantities. So somehow we would like to obtain an expression for this parameter in terms of the input signal S1T and S2T. For that, remember, for a matched filter, we have already seen what is the expression for the maximum signal to noise ratio. Now the output signal to noise ratio for the difference signal here can be directly written from this: S by N is A1 minus A2 whole squared, remember, normalized power, divided by sigma N squared, that is the noise power. So that is the signal to noise ratio. Now when you have a matched filter for difference signals, the filter, remember, is matched to S1T minus S2T. In that case, we have already obtained the expression for the signal to noise ratio in terms of the S1T minus S2T. So that is 2 ED upon N0. Remember, you may have to revise your matched filter we had studied earlier. So that was simply obtained, the maximum signal to noise ratio was obtained as 2E by N0. Now in this case we write it as 2ED because this is the energy of the difference signal. So what we'll do is we'll equate this signal to noise ratio to this and obtain the expression for this parameter. So this parameter then can be written in terms of ED, and ED itself is the energy of the difference signal, which can be written in terms of S1T and S2T, and therefore we'll obtain the expression for the bit error probability in terms of S1T and S2T. Alright, so first order of business is to express this in terms of the energy of the difference signal. So how do we do that? Simply equate this to this and then manipulate. So S by N is A1 minus A2 whole square divided by sigma N square, that is equal to 2 ED by N0. So from this it's easy to see that A1 minus A2 upon 2 sigma N will be equal to square root of ED upon 2 N0. So we have obtained this expression because this is the parameter for the Q function. So now this parameter can be expressed in terms of the energy of the difference signal. And what is the energy of the difference signal? That is S1T minus S2T whole squared integrated from 0 to T. And in that case, the bit error probability is given as Q of square root of ED upon 2N0, where ED is given by this. Now, in order to study this further, we need to obtain the expression for ED by expanding this expression. And then the ED that we will obtain will depend on what is the correlation between S1T and S2T. We'll see that in a minute. So let us do that now. Remember, we started by saying that we wanted to obtain the expression for the bit error probability in terms of S1T and S2T, and that's what we are going to do now. So we have to substitute for ED from here. So let's first look at the ED itself. S1T minus S2T whole square dt. Let's expand this. So this integral S1T whole squared plus S2T whole squared minus 2 S1T S2T integrated. This represents the energy of the S1T over the bit time period. This represents the energy of S2T over the bit time period. And we are going to assume that the signals are such that generally these energies will be same. So if this is EB, we'll assume that this is also same. Now this can be expressed in terms of the correlation between S1T and S2T. So let us first of all define that correlation. So here the rho, which is the cross correlation coefficient, is equal to 1 upon EB. This is because we are assuming constant energy for both the signals, and then product of S1T S2T from 0 to T. So once you have defined your cross correlation coefficient in this fashion, this integral can be expressed in terms of the cross correlation coefficient. So this is EB, this is EB, and it's easy to see that this integral will be rho multiplied by EB, and there's a 2 here, so you get this as 2 EB multiplied by rho. So you combine this, you obtain 2 EB to 1 minus rho. That is, remember, that is the energy of the difference signal. So then bit error probability is now given by Q, and now this is EB into 1 minus rho upon N0. So this means that your bit error probability now depends on the EB, of course, that is the bit energy, that is the energy of the signal representing the bit, and rho is the cross correlation. So this cross correlation will of course depend on the nature of S1T and S2T. So we'll see a couple of examples and therefore see how bit error probability differs for different schemes. Okay. So if you have antipodal signals, S1T is equal to minus S2T, and it will be easy to show that rho is equal to minus 1. This is an exercise left to the student to complete. It will be easy to show that rho is equal to minus 1. If rho is minus 1, then this is minus 1, so that becomes 2, and PB is equal to Q with a parameter under root of 2 EB upon N0. For signals with rho equal to 0, orthogonal signals, it is Q of square root of EB upon N0. So clearly the antipodal signals will have better noise performance. You can see here, because this is 2 times EB, whereas here in the numerator you got EB only. So clearly this parameter is larger and this bit error probability will be smaller. So if you plot bit error probability against EB by N0, okay, which is the ratio of the bit energy and the noise, then you can see that as you go on increasing this, the bit error probability will go on decreasing. And if you plot the two curves, one for antipodal signals and one for orthogonal signals, the result will look something like this. So for a given EB by N0, you will see that for orthogonal signals, the bit error probability is larger, whereas for antipodal signals, where this is your bit error probability, the bit error probability is going to be smaller. So that's all in this session. In this session, we have seen how to express the bit error probability in terms of the received signals S1T and S2T, and we have seen that antipodal signals give better noise performance as compared to the other kind of scheme in which the cross correlation between the two is 0. Okay, so that's all in this session.